Hello, this is Tomoyuki Morimae from Kyoto University. I'm going to talk about proofs of quantumness from Trapdoor Permutations. This is a joint work with Takashi Yamakawa from NTT and Kyoto University. For details, please see this paper. First, I explain what is proofs of quantum. So we have a classical polynomial time Alice and also a Bob. Bob wants to show that he has a quantum computer to Alice. So Alice asks Bob to prove it. Because Alice is classical, they can exchange only classical messages. A proof of quantumness requires the following two properties. First, correctness, which means that there exists a quantum polynomial time Bob such that the probability that Alice accepts is very large. Second, the soundness, which means that for any classical polynomial time Bob, the probability that Alice accepts is negligibly small. Let me explain the first construction of proof of quantumness by this paper. They assume a pair of functions that satisfy trapdoor, injective claw-free property, and adaptive hardcore bit property, which I explain later. So their construction is as follows. The verifier generates a pair of trapdoor and a pair of functions. Trapdoor is kept secret, and these F0 and F1 are sent to the prover. The prover generates this quantum state and measures the third register in the computational basis. The state after the measurement is this state, where x0 and x1 are preimages of f0 and f1 respectively. The prover sends the measurement result y to the verifier, and the verifier sends a single bit c, which is the challenge bit. The prover, if c equals 0, the prover measures this state in the computational basis and returns the measurement result. The verifier, because the verifier has the trapdoor, she can compute x0 and x1. So she checks whether this is correct or not. If this is correct, then the verifier accepts. Otherwise, the verifier rejects. If c equals 1, the prover measures this state in the Adamar basis and sends the measurement result to the verifier. The verifier checks whether this property is satisfied or not. If this is satisfied, the verifier accepts. Otherwise, the verifier rejects. The completeness is very clear. So let me explain the soundness. The soundness is intuitively shown in the following way. So assume that the classical polynomial time prover can correctly answer both these challenges. Then, because this prover is classical, we can rewind this algorithm. So this means that first we run this algorithm, and then we input this c equals 0 to this prover. Then prover outputs this value. And then we rewind the prover before this step, and then we input this c is equal to 1 to this prover. Then prover again outputs this. So this means that classical prover can output both this and this. But the assumption of the adaptive hardcore bit property prohibits this. The adaptive hardcore bit property means that no adversary, polynomial time adversary, can obtain this and this at the same time. So because of this assumption, classical prover cannot make the verifier accept with non-negligible probability. So this proof of quantumness was recently improved by this paper. So they assume trapdoor. They assume some function f, which is trapdoor, and 2-to-1 collision resistant hash. So in this assumption, they no longer require the adaptive hardcore bit property. So their construction is as follows. The verifier generates a pair of trapdoor and function f, and trapdoor is kept secret. The verifier sends only the function f to the prover. The prover generates this quantum state and measures the second register in the computational basis. The state after the measurement is this state, where x0 and x1 are two preimages of this f. The prover sends the measurement result y to the verifier. Then the verifier sends a single bit C, which is a challenge bit, and also a random bit string R to the prover. If C equals 0, the prover measures this state in the computational basis and returns the result to the verifier. Because verifier knows the trapdoor, the verifier can compute x0 and x1, and the verifier accepts if x prime is equal to x0 or x1. If C is equal to 1, then the prover generates this quantum state by using the random bit R. Then the prover measures the second register in the Adamal basis. The state after the measurement is this state. The prover sends the measurement result D to the verifier. Then the verifier sends a certain angle theta to the prover, and the prover measures this single qubit state in this basis and returns the measurement result A. And if these D, theta, and A satisfy certain conditions, then the verifier accepts. The correctness is easy to show, and the soundness is intuitively shown as follows. So because of the collision resistance property, the prover cannot run both x0 and x1. And this intuitively means that the prover cannot know what is his state. So this single qubit state is one of the following four BB84 states, but because the prover does not know both x0 and x1, so he cannot know which state he has. But on the other hand, because the verifier has a trapdoor, she knows which state the verifier possesses. And therefore, the prover cannot cheat by sending this measurement result without generating this quantum state. So this is an intuitive understanding of the soundness. I have explained the previous two constructions of proofs of quantumness. The first construction assumed claw-free property, and the second construction assumed collision-resistant property. So this suggests the following natural question. Is collision resistance really necessary for proofs of quantumness? And the main result of the present talk is to show the answer is no. So we construct proofs of quantumness from trapdoor permutations. Because black box reductions from collision-resistant hash functions to trapdoor permutations are known to be impossible, our result suggests that it is not necessary, collision resistance is not necessary for proofs of quantumness. So before explaining the details of our results, let me give two remarks. So first, most of constructions of proofs of quantumness assume collision resistance property, but there is one exception. So in this paper, they constructed proofs of quantumness from quantum homomorphic encryption. So in classical cryptography, it is known that homomorphic encryption implies the existence of collision-resistant hash functions. However, in their quantum homomorphic encryption, they consider only specific types of quantum operations. And we don't know whether their restricted quantum homomorphic encryption imply collision-resistant hash function or not. The second remark is the following. So we construct proofs of quantumness from trapdoor permutations. But our trapdoor permutation is the full domain, which means that the domain is just the n-bit string, entire space of n-bit strings. So one natural open problem is, can we remove the full domain property? And the reason why we ask this question is the factoring-based construction can be made full domain, but it is not true in general. So for example, the IO-based construction is not full domain. So if we can remove the full domain property, maybe we could construct proofs of quantumness from IO, for example. So now let me explain our construction. So the idea is based on the so-called interactive hashing considered in this paper. So F is a one-way permutation, and let us consider the following interactive protocol between two classical Alice and Bob. So Alice chooses some random bit string H, J, which is chosen as follows. So the first J-1 bits are all 0, and J's bit is 1. And the remaining bits are uniformly chosen at random. And this bit string is sent to Bob, and Bob returns a single bit CJ. And they repeat this interaction from j equal 1 to n minus 1. Then finally, they get this system of linear equations. And you can easily verify that this system of linear equations has two solutions, y0 and y1. And then they showed that no probabilistic polynomial time Bob can find both x0 and x1 such that they are satisfied. So x0 is the preimage of y0 and x1 is the preimage of y1. So they used this idea of interactive hashing for the construction of bit commitment, but we use this idea for the construction of proofs of quantumness. Our idea is executing the interactive hashing coherently. So this F is a trapdoor permutation, and the verifier first generates the pair of trapdoor and function F. So the verifier sends this permutation F to the prover, and also sends this random bit string H1 to the prover. The prover generates these quantum states and measures the second register in the computational basis. The state after the measurement is this state. The prover sends the measurement result to the verifier. The verifier then sends H2 random bit string to the prover, and the prover generates this quantum state from this state. Then the prover measures the second register of this quantum state. The state after the measurement is this state. The prover returns this measurement result C2 to the verifier. So they repeat this process, and finally the prover possesses this quantum state, where x0 is the preimage of y0 and x1 is the preimage of y1. And because the verifier knows the trapdoor, she can compute x0 and x1. And now, from this, we can just run the protocol of KMCVY22 from this stage. And the completeness is very clear, and soundness is also easily shown. So in this KNCVY22 paper, the prover cannot run both x0 and x1 at the same time because of the collision resistance. But here, instead of the collision resistance, we can use this result, which I mentioned in the previous slide. So no probabilistic polymeter involved can find both x0 and x1 the preimages of y0 and y1 respectively. And so instead of collision resistance, we can use this property. And again, this say that both x0 and x1 cannot be computed by classical involved. So we can show the soundness in a similar way as that in this paper. Finally, so let me conclude this talk by giving some open problems. So first open problem is, can we remove the full domain property? So as I said, our trapdoor permutations are full domain. But if we can remove the full domain property, maybe we could construct proof of quantumness from I/O. The second open problem is, can we replace the trapdoor permutations with trapdoor functions? And the third open problem is, can we remove even trapdoor? So for example, can we construct proofs of quantumness from one-way functions? And finally, the fourth open problem is, can we show the quantum security of the interactive hashing? So unfortunately, in this paper, we didn't show the quantum security of Novi because showing this itself seems to be a very challenging problem. But if we can show the quantum security of this Novi protocol, we have many nice applications like quantum money, remote state preparations, classical verification, quantum computation, and so on. Okay, so this is the end of my talk. Thank you very much for your attention. So for details, please see this paper.